Okay, so when we can work out in very great detail what happened during the last 4 ice ages because of drilling cores through Greenland and Antarctica. Because Greenland ice sheet and Antarctic ice sheet gradually build themselves up with layers, annual layers of snow that get compressed into ice. So if you drill right down through the ice sheet, which is a couple of miles thick, you'll go through these layers and you'll go back in history. So it's telling you that the climatic history of the planet is coming out of this ice core record. And ice cores have been drilled through the middle of the Greenland ice sheet and the Antarctic ice sheet. And they both show the same sequence of events. And we know what the temperature was in these ice samples because of there's 2 isotopes of oxygen, oxygen 18, oxygen 16, and when snow falls, the ratio of these 2 isotopes depends on the temperature of the snow. So this is really like a temperature gauge, which tells us the temperature of the planet back through 500,000 years. And the other thing is, which is just when scientists started to drill, they were able to get this temperature record out from the isotopes, but then they got more clever and found that there were tiny little air bubbles in the ice that have, as the snow fell and compressed, little air bubbles were left and got even more compressed. And the air bubbles, if you extract the air very carefully with a tiny syringe, you can measure the carbon dioxide content. So we know what the carbon dioxide content of the atmosphere was back 500,000 years, which is, I think that's an amazing discovery because we can tell what the natural carbon dioxide content of the atmosphere is. And so here we have the top one shows the actual record of temperature. So it even though the Milankovitch variations are a smooth curve, the actual response of the Earth is a sawtooth pattern, and that's because it's easier for glaciers to melt than to form, because a glacier forms by snow falling each winter on some mountain, and it doesn't melt in the summer because the climate's got colder, so it gradually builds up in thickness. So the amount of ice in glaciers slowly builds up, but it can only build up at 1 layer a year. But then if the climate gets warmer, the whole glacier can melt very quickly. So it's possible for the planet to warm up more quickly than it cools down. So here we have these sawtooths where we come quickly out of an ice age. That thing on the left is how we came out of the last one, but we sink slowly towards an ice age. That was the period of the last 150,000 years. Then we came quickly out of that one, and there's the previous ice age, which we sank slowly towards, came quickly out of it, and so on. So we managed the record shows 4 ice ages, but then you get down to the bottom of the ice sheet and you run out of ice. So you can't really go further back than that, but that's quite a long way. And the carbon dioxide record is exactly the same. So first thing we know is that high levels of carbon dioxide in the atmosphere are associated with warmth. We know that today because we're doing the experiment of putting more in and observing that the planet gets warmer. But in the past, there was a natural correlation that when there was a lot of carbon dioxide in the atmosphere, the planet was very cold. And we noticed that the variations between the warm period and the cold period are very similar in the levels of carbon dioxide. That when we're in the middle of an ice age, there's a low level of carbon dioxide in the atmosphere, about 180 parts per million. And then when we come out of that ice age into a warm period, we get up to about 270, 280 parts per million. And it's amazing how similar those two levels are between the interglacial and the glacial. What it means is that the Earth has a natural cycle here, that it goes driven by these astronomical variations, but we go from warm slowly down into cold with with glaciers forming everywhere. The carbon dioxide content slips from 280 to 180, and then we come quickly out of that, and the carbon dioxide content goes right back to where it was before, to 280. Then we sink slowly down again. So when the Earth is in its warm period with minimum ice, the natural level of carbon dioxide in the atmosphere is 280 parts per million. That's the balance between plant life, animal life, the processes that generate carbon dioxide, the processes that use it, respiration or producing it, and transpiration using it. Then when there's less vegetation on the planet and with more ice, the natural level is 180. Then the bottom picture is also, you can extract dust out of these little bubbles, and this just tells you how dry the planet was. And it's not such a good correlation. It tends to show there were a lot of periods when the Earth was very dry with a lot of dust in the atmosphere. But the top two are the main ones, and it was very exciting to see this carbon dioxide curve come out and match the temperature curve for the planet. So that's what we know about the last 500,000 years. Here we are. Oh, no. Anyway, we had this natural tendency to, when we came out of a glacial period, to go up to 280 parts per million of CO2. And this shows the last 10,000 years since we came out of the last ice age. And we can see that up here, the Earth went up to 280, and amazingly it stayed at 280 from 10,000 years ago right to the middle of the 19th century, right to sort of 150 years ago. So the Earth's natural balance, its tendency to want to have a CO2 content of 280, if there's no humans around to screw it up, was maintained right from the end of the Ice Age, from 10,000 BC right up to 1850 AD, and then we started to burn coal, and Trump would approve of that, but we started to burn coal with the Industrial Revolution, and we were, for the first time, we were changing the atmosphere of the planet ourselves by burning coal and having the steam age. And we can see that that had an immediate impact on CO2 levels. So we were up at this sort of 280 level, which was natural, and then about 1850 we started to burn coal, and everything was coal-fired in the early Industrial Revolution. Of course, then we started to burn oil as well, but coal was the starter. And immediately the carbon dioxide concentration shot up. And we know that now from things like records of tree rings and thermometer records. In 1850 there were the beginnings of meteorological institutes, and people were measuring temperatures with thermometers. And so that CO2 content went right suddenly up, and following it was the methane content of the atmosphere, which also had reached some level, natural level, and then shot up as soon as we started the Industrial Revolution. And the bottom one there is nitrous oxide. But the most important gases that have a greenhouse effect are carbon dioxide and methane. So that shooting up uh, initially, firstly, people didn't know it was happening because amazingly, we weren't systematically measuring carbon dioxide in the atmosphere until 1958. Nobody thought to bother to do it. And then there was an observatory built on Mauna Loa by Scripps Institute of Oceanography, and they've been measuring CO2 there and then lots of other places ever since. But until 1958, nobody was measuring it. But it had been predicted in 1896 that the CO2 levels should be rising and that this would have a global effect. And so this was a really far-sighted prediction. But the prediction, the person who predicted it said, well, we don't have to worry about that because it'll all be absorbed by the oceans. And everybody said, oh, fine, okay, nobody bothered to measure it. So for about 50 years after we started to mess up the atmosphere, we didn't know that, firstly, we didn't know that we were doing it, and secondly, we didn't have any basis to calculate why we were doing it. Then in 1896, there was the first paper on what was going on, that we were changing the radiation balance of the planet, but he didn't seem to really think it was too serious. Now we know it is serious and we're measuring it. So it took a long time. So there was some excuse for us doing nothing about global warming for the first 100 years, which was either that we didn't understand the theory by which global warming affects the planet for 50 years, and then for another 50 years we understood the theory, but we didn't have any measurements because nobody was bothering to measure CO2 levels. Now we haven't got any excuse, but since 1958, but we still not doing anything very much. Okay, let's. Okay, well, this warming of the planet obviously is going to affect a lot of different aspects of the planet, and so the first one that I'm going to talk about is sea ice, and it was very difficult to measure ice extent in the Arctic because until about 1950, 1960, because there were only a very few explorers would go into the ice, and there were a few in Scandinavian sealers and whalers would work around the edge of the ice and send back reports on where the ice edge was. So there was, with enormous difficulty, it was possible to get some idea of ice extent in the Arctic. And then after about 1950, there started to be regular airborne patrols mapping the ice limits. The Air Force, navies, the US Navy, and then a lot of meteorological institutes in Canada and Europe were flying aircraft. And then after 1970, satellites took over, and now it's very easy because you just look at a satellite picture, you can see exactly where the ice is because it's white, and you can measure it. So we have very exact pictures now of how much ice there is in the Arctic. But peculiarly, the retreat of ice in the Arctic in summer seems to date from about 1950. So I'm a bit suspicious of that because I think all the measurements done before 1950 are suspect. But once we started to be able to do measurements, we saw the ice going down in area. So the brown curve here is the ice in summer, during the summer months, and that's was decreasing fastest. The other curves show the ice during other seasons of the year. And it seems that in other seasons the ice wasn't decreasing so much, but that's because in the winter the whole of the Arctic Ocean is frozen right to the coastline of North America and Asia, and some more besides in Bering Sea and Greenland Sea. So if the climate improved, or got warmer rather, there wasn't scope for the ice really to retreat. It still wanted to be right up against the coast. So in winter, you didn't see a decrease in ice area, but you did in summer because the ice moved back a little way from the coast. So we have this brown curve, which is the summer ice extent, becoming noticeably decreasing from about 1950 onwards. And okay, I keep pressing the wrong button here. Okay, so it wasn't all that noticeable at first, but then gradually, as I said yesterday, with exponentials, you don't notice anything is happening, then everything seems to happen suddenly. And that happened with the ice extent. And in 2005, it was the first year, which is not long ago, the first year in which the ice really moved back a long way from the coastline in the summer. So instead of having an Arctic Ocean that connected up Europe and North America and Asia with one great solid slab of ice, we have an Arctic Ocean which is a real ocean in summer. And so the pink line here is the average over the previous 30 years of where the ice edge lay in September. That's the month of greatest retreat. And so that's still lying close to the coastline. Then in 2005, it had retreated far enough that you've got a very big slot right across the north of Russia and across the north of Alaska and through the Canadian Arctic. So it was possible for a ship to sail across the Northeast Passage, the Northern Sea Route, north of Russia, and get from Siberia across to Europe without hitting any ice. And to a lesser extent, you could do the same with the Northwest Passage. So 2005, suddenly the world discovered two new sea routes that weren't there before, the Northern Sea Route, north of Russia, and the Northwest Passage, as being routes that you could send ships through, send merchant ships. So that was 2005, the first year in which the Arctic sea ice really shrank to a level where you thought of it as a floating mass of ice instead of a solid mass of ice connecting the two continents. Then 2007, a huge bite got taken out of it, and it retreated even more. So the Beaufort Sea, which is the area north of Alaska, between Alaska and North Pole, suddenly became a blue sea. And as somebody said yesterday, this era, you started to be able to see blue if you looked at a satellite picture of the Earth from space. The top end of the Earth in summer suddenly started to look blue instead of white. So we were changing the appearance of the planet. And so there in 2007 we had then a huge sea, sort of it's as which is half the Arctic Ocean, became ice-free. And so that was when sort of people first started to appreciate that the sea ice is disappearing. But I guess I'd been warning them for about a decade or two from measurements that were done from submarines that the ice was getting thinner, so and they should expect it to start vanishing. But it came as a surprise to everybody when it actually happened. Okay, then 2012 it retreated even more, and the yellow is the 2007 summer ice edge, and then the white is 2012. So it lay even further back. Again, in the Beaufort Sea, there was another big retreat, but there was also a retreat to the north of Russia. So 2012 remains the record, just about. Since then, it's sort of hung about that limit, but it's got less in all the other seasons of year. So the volume of ice, the area of ice is continuing to decrease all the time, but that little kind of September minimum, it's still holding out, and it hasn't yet gone away, but it probably will pretty soon. So that's Okay. uh, that's what the ice has been doing. And we can relate that back to global change. But the question here is, why is the Arctic ice retreating so fast compared to other aspects of our climate in the world? We don't see other things changing as fast as the Arctic is changing. And the reason is that the Arctic is warming up about 3 times as fast as any other part of the world. And we can see that because this famous curve, which climate change deniers put an enormous amount of effort into discrediting this curve. And it's called the Mann-Bradley curve of the world's temperature over the last 1,000 years. And it's called a hockey stick curve because, as you can see from the bottom, the world in the year 1000, when there was the Viking colonies in Greenland, the world was slightly warmer than it later became, and then the average temperatures over the Earth gradually got colder until again 1850, and then suddenly they shot up again, and that was the Industrial Revolution. So this hockey stick curve, which looks like a hockey stick, it's clear that it's the Industrial Revolution and the release of carbon dioxide from burning fossil fuels that produced that huge jump, and before that, over 1,000 years, you just had minor fluctuations due to sort of random changes. And this is the best record we've got. They used every possible measurement. There were, thermometers going back about a couple of 100 years, and before that, measurements of tree ring growth, measurements from corals, ice core measurements, the top parts of these ice cores. And so this is a very reliable curve, and therefore it had to be discredited because it showed it very clearly that it was the Industrial Revolution that produced the big warming of the planet. And so, in fact, the climate change deniers appointed some of their own cronies to re-examine the data, hoping that this would prove, this was funded by the Koch brothers, that this would prove that this was yet another hoax, possibly Chinese, and but unfortunately for that they found that it was actually correct, and this data still stands, and even the people who did that study on behalf of the climate change deniers still said, no, this is true. And so there it is, this is what's happened. If we blow up the last 150 years, which is the top curve, we see that the Earth was warming up quite fast, but it did pause or go back a little bit between 1940 and 1970, and then it took off again. So that's something that needs to be explained. But we can see that the warming from the middle of the 19th century until today was about 0.8 of a degree. That's the average temperature of the Earth. So the global warming, man-induced global warming from the Industrial Revolution has been about 0.8 of a degree so far. But when you look at, that's the world as a whole, but when you look at the Arctic, which hopefully we can look at in a minute. But there we are. Okay, when we look at the Arctic, and this is just since 1900, and compare it with that previous curve, I showed that the top curve showed that the planet really warmed up rapidly, stopped warming, and then took off again. Now, if we just look at the data from north of 60 degrees, this is data from weather stations between 60 degrees and the North Pole, then we see the same pattern, that the world warmed up rapidly. It went back a little bit from 1940 to 1970, then it took off again. So we see the same shape, the same response in shape, but a different magnitude. Instead of warming by 0.8 of a degree, it's warmed by about 3 degrees. If you look at from -2 to +1 and a bit. So it's the same shape of change, but the magnitude of the warming in the high northern latitudes has been about 3 to 4 times as great as the warming of the planet as a whole. So the Arctic is taking off and warming itself much faster than any other part of the world, and that's the reason why the ice is retreating so fast. Well, okay. This is actually the amount of warming we've had in this case since 1950 at different latitudes, and we can see that if the average, the Arctic is warming much faster than the global average, several times as fast, and of course the rest of the planet is warming at less than global average to offset that. So we really have a strange thing going on in the Arctic called Arctic amplification, and we're getting a more rapid warming, but which is not fully understood what's causing that.